So what is the value of J? So J is actually has a numerical value that we use mathematically to help us manipulate relationships with the square root. So if you multiply the positive real value of plus 2 by J, the result becomes plus J2. This multiplication has effectively moved the plus 2 through 90 degrees of angle to the plus J axis. So we've rotated it off of the horizontal and onto the vertical. Well, how do we do that? Similarly, multiplying plus 2 by minus J rotates it down to the minus 90 degree, to the minus J axis. So J is considered to be a rotational operator. Mathematically, the J operator has a value of the square root of minus 1. If plus J2 is multiplied by J, you get J squared times 2, which is equal to the square root of minus 1 times the square root of minus 1 times 2. So when you multiply the two square roots together, they disappear. You get just minus 1 times 2, or a value of minus 2. So you can see it has a mathematical significance here, and it operates mathematically. This calculation effectively places the value on the negative real axis. Therefore, multiplying a positive real number by J squared converts it to a negative real number, which in effect is a rotation of 180 degrees in the complex plane. This operation then is illustrated in the diagram below. So you can see below what actually happens with the change in angle. So we need to understand and be able to maneuver between the rectangular, Cartesian, complex plane, whatever, and the polar forms. Rectangular and polar forms of complex numbers are two forms that are used to represent Phasor quantities. Each has a certain advantage when used in circuit analysis, depending on its particular application. Sometimes it makes it easier to operate in the polar form than the rectangular form. A Phasor quantity contains both magnitude and angular position or direction. In this case, in electronics, we call it phase. In this text, italic letters use the capital V and the capital I to represent magnitude only, and bold-faced non-italic letters such as bold-faced V and bold-faced I are used to represent complete Phasor quantity. So you need to get used to that. Look at which values you're using. Are we using an instantaneous value of voltage and current with the parenthetical T behind it? Are we using the italic V and I to represent magnitude only? Or are we using the Phasor representation V and I bold-faced? Rectangular form then for a Phasor quantity is represented in rectangular form by the algebraic sum of the real A value of the coordinate and the J or B value of the coordinate system. So we have to learn how do we operate and add, multiply, subtract, divide using these individual coordinates on the X and Y axis. So we use the general form A plus JB. In your math class, you probably saw little a plus BI for the representation. So we're going to use A plus JB in electronics. Examples of Phasor quantities then are 1 plus J2, 5 minus J3, minus 4 plus J5, minus 2 minus J6, which we saw in the last example. These are shown in figure 15.9. So as you can see, the rectangular coordinates describe the phasor in terms of its values projected onto the real axis and the J axis. An arrow then is drawn from the origin to the coordinate point in the complex plane, and it represents graphically the phasor quantity. In polar form, we look at it a little differently. Phasor quantities expressed in polar form consists of phasor magnitude, in this case c, which becomes the hypotenuse of a right triangle, and the angular position relative to the positive real axis, in this case the angle theta, expressed in general terms. So we have c at an angle plus or minus theta. Examples there again then are 2 at an angle of 45 degrees, 5 at an angle of 120 degrees, 4 at an angle of minus 110, and 8 at an angle of minus 30 degrees. So graphically we can see that in the figure 1510 for each of these examples, where they actually plot out on the real and imaginary axis. The length of the phasor, of course, represents the magnitude of the quantity. This can be drawn out on a piece of graph paper, where you let the length of the size of the squares, the graphical squares, match with the corresponding magnitude. But we're going to do them all very, very simply here. Sometimes you mark it and just say not drawn to scale. Keep in mind that for every phasor expressed in polar form, there is also an equivalent expression in rectangular form. So we need to learn how do we move back and forth between polar and rectangular. You can see here below in 1511 they start to give us what goes on in terms of the angles in each of the quadrants. So you need to pay attention to that as we move forward. Conversion from rectangular to polar form, then a phasor can exist in any of the 4 quadrants of the complex plane as indicated below in 1511. The phase angle theta in each case is measured relative to the positive real axis. Okay, so it's relative to the x-axis, 0. And phi is the angle in the second and third quadrants relative to the negative real axis as shown. So you can see you can have angle theta or you can have angle phi. In each case you have to deal with the sign of the angle. The first step to convert from rectangular form to polar form is to determine the magnitude of the phasor. A phasor can be visualized as forming a right triangle in the complex plane. The horizontal side of the triangle is the real value A, and the vertical side is the J value B. The hypotenuse of the triangle is the length of the phasor C, representing magnitude and expressed using the Pythagorean theorem as C is equal to the square root of A squared plus B squared. Next, the angle theta indicates in part A and D of the figure 1512 is expressed as an inverse tangent function. So that little -1 there by the tangent, that is telling you it's an inverse tangent. So we're taking the opposite of this ratio B over A, plus or minus B over A. We take the inverse tangent. What we get back is, in fact, the angle. The angle theta indicated in parts B and C of the figure 1512 then is theta is equal to plus or minus 100 degrees minus plus the angle phi, in which includes both conditions as indicated by dual signs. Okay, so we have that representation plus minus minus plus, in this case the inverse tangent of B over A. In each case the appropriate signs must be used in the calculation. The general form for converting from rectangular to polar then is plus or minus A plus or minus JB is equal to C, the magnitude, at an angle of plus or minus theta. So in figure 15.2, 12 here, then we can see what happens in each case. First quadrant, second quadrant, third, and fourth. And the relationship with the Pythagorean theorem and the right triangle that we are now developing in polar form. Okay, so you need to get used to seeing these, and you're going to use these conversions and this representation a lot. So if we look at an example here, converting the following complex numbers from rectangular to polar by determining the magnitude and angle. So we have a rectangular and A, 8 plus J6, and B, 10 minus J5. The magnitude of the phasor represented by 8 plus J6 then is, first step, use the Pythagorean theory. The hypotenuse C is equal to the square root of a squared plus b squared. So we take the real part, 8 squared. We take the imaginary part, 6 squared. When we square those and add them together, we get 100. Take the square root, we get a magnitude, in this case, in polar form of 10. Now, since the phasor is in the first quadrant, we use equation 15.2. The angle then becomes theta is equal to the inverse tangent plus minus b over a. In this case, it's 6 over 8. Okay, b is the 6, a is the 8. And when we take the inverse tangent on our calculator, if you're using your calculator, there's a key here that allows you to do an inverse tangent. You look at tangent, there in a subscript it says inverse tangent. You'll have to use probably a shift key. Okay, in doing that then, we get C, angle theta, is equal to angle 36.9. We do the same thing with the second example, 10 minus J5. Apply the Pythagorean theorem. We get an angle of we get a magnitude of the square root of 125, which is 11.2. We find the angle theta is equal to the inverse tangent of minus 5 over 10, which gives us a minus 26.6 degrees. So theta is the angle relative to the positive real axis. The polar form 10 minus J5 then becomes 11.2, the magnitude, at an angle of minus 26.6 degrees. To go the other way, conversion from polar to rectangular, we start with that right triangle relationship. C is the hypotenuse. The imaginary side, B, is C times the sine of theta. The real part is A, C times the cosine of theta. So to get the rectangular form, you must find sides A and B of the triangle, the right triangle, using the rules from trigonometry. A is equal to C cosine theta. Side B is equal to C sine theta. The polar to rectangular conversion then is C, the magnitude at an angle theta, is equal to A plus JB. So if we look at an example, we want to convert 10 at an angle of 30 and 200 at an angle of minus 45. So the first thing we need to do is decompose what's going on here. We've got 10 at an angle of 30, so side A is equal to C cosine theta, or 10 cosine 30 degrees, which gives us 8.66. The J part, then the B part, is JC sine theta, which is J10, the sine of 60 degrees. When we multiply that, we get back our B component, J5. So the rectangular form of 10 at an angle of 30 degrees then is 8.66 plus J5. If we do the same thing for example B, again we're starting at 200 at an angle of minus 45. Decompose it into its A and B sides, real and imaginary. For A, we get 144. For B, we get minus J 144. So that is our rectangular relationship. A plus JB is equal to 141 minus J 141. So When we come back, we're going to look at handling mathematical operations. What if we want to combine complex numbers together, both polar and rectangular? Well, there are rules and there are easy ways and hard ways to do it. So the first thing we're going to look at when we come back is how do we add complex numbers together in rectangular form.